Alrighty, today we'll be talking about resting membrane potential in a cell and in neurons. First, the important thing to understand is that there is ion flow in the cell, inside and outside, and the primary two ions that we'll be talking about today is sodium, NaCl, and potassium, or K+. Now, the way that the cell can have a negative resting membrane potential, and typically it's at -70. The way this happens is by a few methods. The first thing we need to understand is that the cell has a bunch of these sodium-potassium pumps. And that's a little diagram of it right there. Now, these are all along the membrane. They're not just in this one spot, but there's a bunch all on the membrane. And what they do is they pump 3 sodium in, or I'm sorry, they pump 2 potassium into the cell and 3 sodium out of the cell, as shown here. And so what this does is it creates a chemical gradient, right, where there's a lot of sodium outside the cell and a lot of potassium inside the cell. Now, particles and ions always want to move to the place where there's less of them, right? And so this potassium naturally wants to leave, and this sodium naturally wants to come in because of this chemical gradient set up by the sodium-potassium pump. And the thing is the sodium can't really enter most of the time. The cell is practically impermeable to sodium, or at least we pretend it is for all intents and purposes when we do physiology problems. And potassium can leave the cell. And this is because of these leak channels that are all along this membrane. You'll see these little black openings right here, all along the membrane. Those are potassium leak channels. Now, the sodium-potassium pump creates a chemical gradient, and what creates the voltage difference is actually these channels that allow the potassium to leave. Because what happens is potassium wants to go down its chemical gradient and leave so it can join the lonely guys out here of potassium, and it will do so, right? And so slowly the amount of potassium in the cell will be going down and decreasing. And this makes the cell more negative because there's less positive charges within the cell to offset the negative charges that are already there. Now, these negative charges can come from ions, but a lot of times they're just proteins that are negatively charged. And so the cell, if we were to have a graph right here, as potassium leaves, then the cell's resting membrane, or the cell's membrane potential, right, or the cell voltage goes down. Now, one would think then that the potassium would just leave really, really fast, and then it would get to the point where there's half potassium outside the cell and half potassium inside the cell. But that's not the case. The first reason for this, right, is the sodium-potassium pump that's establishing this chemical gradient. But the other thing we have to take into account is that there is also an electrical gradient that is being established here, right? Where as the potassium leaves the cell, there's going to be more and more positive charges outside the cell. And there already is a lot of positive charges because of the sodium that's outside the cell. And so these positive charges are actually all repelling each other, and they repel the positive charges of the potassium that's trying to come out. So you have this electrical gradient that's trying to force the positive charges back into the cell, and this chemical gradient that's trying to force the charges out of the cell. Now, these effects eventually reach equilibrium. And what equilibrium means is that the rate of potassium leaving the cell and the rate of the potassium entering the cell is the same. And so the voltage stays consistent. Now, this doesn't mean that the ions aren't moving. The ions are moving. They're always moving, but they're just moving in and out at the same rate. and so the voltage stays consistent. Now, what determines how high this voltage is, right? Why is it at negative 70? Now, the reason for this is it can be shown to us by the Nernst equation. And this is the Nernst equation right up here. And this helps us understand what the electrical chemical gradient, what it would be if the cell was completely permeable to this ion, right? So if all factors excluded, if there was only potassium inside the cell, then what would the cell be at? What would the voltage be when this equilibrium is established? Now for potassium, it ends up being around negative 95. If we take sodium into account, say sodium, say we want to see what sodium's would be, that would be a different number, right? It'd be around plus 55 for sodium if it was completely permeable. And this is done by plugging in numbers into this equation, right? This Z here is just the charge of the ion, so it'd be positive 1, and then you take the log of the amount of chemicals inside and then the amount of ions outside of the cell. And you do this math to figure out what the Nernst equation would be for that particular ion. And what that tells us is what the membrane potential would be if the cell was completely permeable to this ion, right? But the fact of the matter is it's not completely and only permeable to one ion. So in order to actually know what the membrane potential has to be is something we have to use this Goldman's equation. And this takes into account every ion. So it's negative 61.5 times the log of, and then you have this big, huge thing that takes into account the permeability of the ions as well as the concentration inside and outside the cell. And it takes into account multiple ions. And this is much more true to real life. And so what the Nernst equation can tell us is that, well, hey, if the Nernst equation or the equilibrium potential, right, of potassium is negative 95, and the cell's actual membrane is negative 70, well, then we can see that the cell is much more permeable to potassium compared to sodium, where sodium would be positive 55. And so it would be a lot more positive if it was more permeable to sodium. But it's not. It's more permeable to potassium. And so the cell membrane potential is more negative. All right. I hope that makes sense. So potassium leak channels establish the voltage. The sodium potassium pump establishes the chemical gradient for that. Now, another formula that we can use to calculate how potassium and how sodium will move is driving force. Now, this is important because if we open a new leak channel, this will change the amount of potassium that is able to leave the cell, thus influencing the rate of diffusion of potassium. And then there would have to be a new gradient. There would have to be a new equilibrium established, and that would change the membrane potential. So we can anticipate how the membrane potential will change if we know what the driving force of the potassium is to leave or to come in. And the driving force is shown as the voltage of the membrane minus the equilibrium potential using that Nernst equation of the ion. All right. And that helps us understand how the ions would move. For example, the driving force of, say, sodium, if we have a driving potential of sodium, the voltage of the membrane is negative 70, and of sodium is approximately positive 55. So the driving force of sodium would be negative 125. Now this means that this roughly is talking about the inside of the cell, and so because it's negative, that means that sodium being a positive charge is attracted to the negative charge. So sodium wants to come into the cell, at a magnitude of 125 millivolts. Or that's the potential energy, right, stored by sodium wanting to come in. Now, for potassium then, it'd be negative 70 minus negative 95, or negative 70 plus 95, right? And so that would equal around positive 24 millivolts. Yeah. So this tells us that potassium is actually repelled from the cell and it wants to leave. And what's the magnitude of it wanting to leave? It's positive 24. So we can see here that if there were to be a channel opened that allows both sodium and potassium in, the magnitude of sodium's driving force is considerably larger. So sodium would outrun potassium, per se. So that's a quick discussion on the driving force right there. Yeah, and this is how the resting membrane potential is established. We can think about how changing these factors would influence the resting membrane potential. For example, if we increased the amount of if we increase the amount of potassium concentration here outside of the cell, that means there's more potassium here than normal. Then that makes it even harder for the potassium to leave, right? And so that would affect the RMP and actually make the RMP higher. And this is called depolarizing. And it makes it more positive because there's going to accumulate more positive charge within the cell, counteracting more of that negative charge, because the potassium doesn't want to leave as much. Yeah, the driving force of potassium decreases because there's a higher concentration outside the cell. And you can see that from the Nernst equation right here, right? How the concentration outside the cell does affect the equilibrium potential, which would then affect the driving force. Now, let's move on to talking about action potentials. Now, an action potential looks like this. Isn't this beautiful? So this is the graph of what the voltage of the cell looks like as it goes through a action potential. Now, an action potential is a fancy word for saying that it's for a neuron firing, right? And what happens during a action potential is there has to be some sort of a stimulus. So say that there was a pressure, there was a mechanically gated channel right here, and whenever someone touched you, right, that pushed on the cell, thus affecting this mechanically gated channel and makes it open, and then a bunch of positive charges rush into the cell. Now, that's a stimulus, right? That would cause the cell to depolarize or to go more positive, right? This is called depolarization. And if that change in voltage is high enough to reach threshold, which is negative 55, then it will cause an action potential. It's like an all or nothing ordeal. Now, the way that threshold is determined is it's the point at where voltage gated sodium channels open. And we can go over here to this drawing right here and zoom in a little bit to see what happens when these voltage gated sodium channels open. So we have the calcium that forms a little spring all along this channel, and it's a positive charge, right? And so what happens is it's being repelled by the outside positive charges, and that makes the spring relax and go down, and it closes this gate. Now, these negative charges are also attracting the calcium down to also close the gate. And so you can imagine if there becomes less negative charges within the cell and there's more positives within the cell, then that will repel the calcium and cause this spring to move up, and that will cause the sodium gated, or this voltage gated sodium channel to open. Thus, as the cell becomes more positive, it causes this voltage gated channel to open, and that's what causes an action potential. So you have this initial stimulus, and this is called a graded potential. A graded potential really is anything that's not an action potential, but still depolarizes the cell. And so a graded potential is what this mechanically gated channel was doing over here. And these graded potentials can add up on each other, right? So if there's a mechanically gated channel here that allows positive charges to rush in, and then if there's another one that's right here on the membrane too, and the same thing happens there, and then the same thing happens over here too, that would be multiple graded potentials that added together to then cause an action potential, because it depolarized the cell up to a threshold. Then when that happens, this sodium gated channel, this voltage gated channel opens, allowing a bunch of sodium and positive charge to rush in. And this continues to depolarize the cell quite rapidly. And you see this rising phase right here where it depolarizes up to a very high point. And then what happens is this voltage gated channel, this ball right here, actually swings in and sits right here and deactivates that channel. So it's open for a few milliseconds to allow a rush of sodium, and then it closes. And that's what causes this sharp incline, this big depolarization right here. Now, why does it go down afterwards, you might ask? The reason why is because there's also voltage-gated potassium channels. And we can have this one as an example. I doubt that's what it actually looks like, but say that's a voltage-gated potassium channel. Now, the thing about the voltage-gated potassium channels is they're a little lazy, and they open a lot more slowly. So, say at this point right here where I put this arrow, the voltage-gated sodium channel would still be open. And maybe this ball is starting to rush in to deactivate it. And this potassium channel is just barely starting to open. It still opens at the same threshold as the sodium does, but it's just really, really slow. And so they're starting to open as the cell's depolarizing, but they just can't keep up. And so once the sodium channel gets deactivated, then this potassium channel is finally open all the way. And that allows a rush of potassium. Sorry, I do that the wrong way. Causes a rush of potassium to leave the cell. And as we talked about earlier, right, if more potassium leaves the cell, that causes the cell to go more negative, and that causes repolarization. Now, the way I think about this is polarization, right, means that you're on opposite ends. And so if you're polarized in a cell, that means that the voltage is more negative. And if you're depolarized, that means you're getting closer to zero or beyond. And so that's what this is. You first have this resting membrane potential. Starts here, and then there's a little graded potential that allows a slight depolarization, and then that begins excuse me, a huge action potential. And then the sodium gets inactivated, the potassium channel finally opens all the way, and it repolarizes. Now, because the potassium channel is so slow, right? Once it once this threshold hits, then it starts to, once you go back underneath threshold, then it starts to close, but it's just so slow. And so it's slowly closing, but that there's still potassium that's able to leave. And so that causes the membrane to hyperpolarize. Right there. Yep. So that's the step, and then it goes back and it returns to normal. Now, why is this important? This is important because whether or not the gates are deactivated or not, or whether or not they're open, determines whether or not another action potential can be sent. So, for example, from here to here, right, along this line, this is when the sodium channel is inactivated. And that means that sodium can't come into the cell. And so this means that no matter how much of a stimulus there is again, there will be no other action potential at this time because the sodium gates are inactivated. Now that's called the absolute refractory period. Yeah. Now, the point from here to here, it's also a lot harder to make an action potential. But the reason why is because sodium is still rushing out of the cell. And so it's hyperpolarizing. The membrane's hyperpolarizing, right? But the sodium channels are not inactivated anymore. They're closed now at this point. And so you could potentially get another action potential. You would just need a lot more oomph, a lot more push, a lot higher of a graded potential in order to get another action potential to start because the cell is hyperpolarizing. And that is called the relative refractory period. Yeah. So that is all about action potentials and about this ion movement. And I hope that makes sense in terms of how the potassium moves and the channels work and everything like that. Another important concept that we need to go over is capacitance and the length constant. And this is all about how action potentials are propagated. Because in reality, neurons don't actually look like that. What happens is there's a huge long axon right here, and there's a bunch of action potentials happening throughout this entire thing, and that's what allows the signals from our brain to travel all the way down to our toes. Now, in order to make this faster, the cell utilizes a couple of different things. First off, conductance. Now, conductance is the charge separation per volt. What this means is that it's how much charge is required for there to be the same amount of potential energy or voltage. And so, if the charges are closer together like this, then more of their electric field is being absorbed by each other. And so, what this means is actually there's less voltage and less potential energy stored here. Whereas over here, these charges are a lot further apart. They're not absorbing each other's electrical field as much. And the draw for them to come together is a lot higher. And they really want to. And so there's a lot more potential energy or voltage stored here. And so capacitance is how much charge separation is required for the same amount of voltage. And this is really, really neat because the cell can then change how much voltage or how quickly voltage can change based on how much charge, based on the capacitance. Because if there is more charges here, then adding another charge doesn't make a huge difference in the voltage. However, over here, if we add another charge, look at that, you just double the amount of charges. And so that increases the voltage a lot more. So this means that influx and efflux of ions like potassium and sodium, a little bit goes a long way when the capacitance is low. Now, this is great because then that means you can have less channels to accomplish the same purpose in voltage change. And so the cell actually uses myelin, the body uses myelin to help facilitate this, where myelin is basically a big fatty covering over the neuron. And so that separates these charges, and it has very low capacitance. And so there can be less charge separation per volt. Now that also means that there's not like any channels along this myelin. Where there's myelin on the cell, there's no channels. Whereas over here, where there's no myelin, there will be channels. Now this goes back to something called the length constant. Now the length constant is how far the electrical field of an ion can be felt. And so if we have a action potential happen, say right here, right? And so all of the sodium wants to rush in, then this amount of positive charge over here will then depolarize another portion of the cell and cause another action potential, and that'll keep going and keep going. Now, if this length constant, if the electrical field can be felt further along, that means that the signal can travel faster and happen and travel a longer way using less action potentials, and that's very helpful. And so the length constant, if we can make that as long as possible, that's great. And if we can keep capacitance down, that's awesome too, because then the cell has to do less work. So the length constant, or lambda, is determined by Rm and Ri. Now Rm is the resistance of the membrane. I guess you can see that, right? Rm, resistance of the membrane. And that's really how much resistance there is for an ion to come in or for an ion to come out. And so the resistance of the membrane goes down when there's more influx and outflux of ions, right? When ions can move more easily. And so hopefully you can see here that myelin then has a very high Rm because there's no channels here, right? And so the resistance of the membrane along the myelin is very high. Now, that's great. That increases the length constant. The positive charge can be felt for longer. It can continue all the way along the myelin, and then another action potential can be sent, and it can travel a lot faster. Now, another thing that's great is myelin typically doesn't have very high Ri, which is internal resistance. And internal resistance can be imagined this way, where say you have a lot of negatively charged proteins right here, well then those would absorb the effect of the positive charge's electrical field, and then the length constant, right, or the amount that this field can be felt goes down. And so the higher the internal resistance, the lower the length constant. And you can see that by it being inversely proportional right here in the equation. And so myelin, right, there's not very many channels along the membrane, and there's not very many things underneath the myelin. And so the internal resistance is low, and the resistance of the membrane is high, and the capacitance of myelin is low. And so a little change in the ion movement can cause a big change in voltage and cause an action potential. And so myelin is very helpful for transferring signals faster along the axon. And I believe that's all that we had to go over. Thanks.